So in this video, we're going to talk about pH. Now, in many fields, whether it be medicinal or chemistry or whatever the case may be, it's really kind of important or necessary for us to know the concentrations of the hydronium. All right. For us to know the concentrations of hydronium or the concentration of hydroxide. All right. Like, so for example, if you're talking about blood, all right. So it's really important for us to know what's the concentration of hydronium in blood, and if the concentration in blood it's of hydronium, right? If it's slightly higher than 4.0 times 10 to the negative 8, you could die, right? And it's important for doctors, nurses, and everybody to kind of know that. But it's kind of weird, using or throwing this number around, right? Because it's a very small number, it's an awkward number, whatever the case may be. So we use the pH scale, all right? Because the pH scale somewhat simplifies things. But let's kind of talk about what does it mean and what does it tell us, all right? Well, so first of all, P is a logarithmic a scale, all right? Or it's a logarithmic function. Let me say it like that. So mathematically speaking, it's defined as a negative common logarithm of some type of variable. Okay, so P is equal to negative log of something. That's what P means. All right, and so when you have pH, all right, it's basically the negative log of the concentration of hydrogen ions. That's what the pH means, or hydronium ions. Doesn't matter, one are the same. All right, but so pH is a logarithmic calculation. All right, and so the pH, basically the scale of pH that we use is between 0 through 14. All right, where 7 is considered neutral. All right, anywhere above 7 you have a basic solution. Anything below 7 you have an acidic solution. All right, so this is your pH scale altogether. So kind of putting this back into play of this of the definition of pH. So as I said, pH is basically the negative logarithmic of the concentration of hydronium or hydrogen ions, or on the flip side, if you were to try to figure out the concentration of the hydrogen ions, is equal to 10 to the power of pH. All right, because log is the common logarithm, which means that everything is just to the power of 10. All right, and so in this case, the hydronium ion concentration is equal to the 10 to the power of negative pH. So what does this mean? All right, this simply means that if you have H3O, right, and you find that the concentration is 1.00 times 10 to the negative 7 molarity, that's the concentration. Well, if that's the case, then the pH of this substance is 7. Okay, and then ultimately, if it's 7, then we know that this is neutral. All right, if we're talking about maybe like a strong acid, where the hydronium ion is 1.00 times 10 to the negative 1 molarity, then the pH is equal to 1. That's your strong acid. Versus your strong base, if it was like the hydronium concentration was equal to 1.00 times 10 to the negative 14 molarity, well, then we know the pH to this is 14. All right, so that gives us an indication that this substance is a base. So when you consider the ranges, right, if you're talking about an acidic solution, all right, remember the pH has to be less than 7. All right, and if you think about the hydronium concentration, it must be greater than 1 times 10 to the negative 7. Okay, if you're talking about a neutral solution, all right, its pH is equal to 7, the hydronium concentration is equal to 1.0 times 10 to the negative 7. All right. And then if you're talking about a basic solution, all right, its pH is greater than 7. All right. And the hydronium concentration is actually less than 1.0 times 10 to the negative 7. All right. So that's the way that you kind of need to think about this. Now, I want you to keep something in mind, though, when it comes to the pH scale and how that relates to the concentration of the hydronium ions. Okay. Now, in order to change, so if you were to change the pH by 1, all right, I would say equals to 1. Let me say by 1. All right. By the definition of what pH is, being a logarithmic by 10, this means that the concentration must be changed by 10 folds. The concentration of hydronium, all right, so if you're talking about the concentration of hydronium, it must change by 10 fold, all right? So what do I mean by that? Now, I could actually show you an example of this. So let's just say that, you have HCl, right? Hydrochloric acid. And then you have the concentration to be 0.1 molar. All right. And if you were to calculate the pH for this, right? And so since hydrochloric acid completely dissociates, right? So then we know that the concentration of hydronium in this case is also 0.1 molar, right? And if you were to calculate the pH, well, pH is equal to negative log of 0.1. All right, you put that in a calculator, you see that the pH is 1. Now, if you wanted to increase the pH, right? So you want that the pH to be 2, okay? How will this affect the concentration of hydrochloric acid? Well, it will have to be affected 10 times. All right, so it's not like if you half the concentration of this, then you're going to have a pH of 2. No, you're going to have to either change the concentration by 10 folds in order to see a change of pH. And so what I mean by that, if we have hydrochloric acid, right, and the concentration was 0.01, so I decrease the concentration of hydrochloric acid by 10, right? If I do that, then we know the concentration of hydronium is equal to 0.01 molar, right? And so if you put this in the calculator, so your pH equals to the negative log of 0.01, we see that the pH of this is 2. All right. And so we see that the change here between 1 and 2 had to be a change by 10-fold of the concentration of the hydronium ion. All right. And so you have to kind of keep that in mind, that this is a pretty large or enormous range in the acidities, because it's a logarithmic scale. All right, so everything in this case always gets changed to the power of tens and not necessarily by halves or double or whatever the case may be. Now, one more aspect of this that I want us to kind of explore, going back to when we talked about Kw, right? Looking at the concentrations of hydronium versus hydroxide, and it's equal to the constant Kw. So Kw is equal to the concentrations of hydronium times the concentration of hydroxide, and we said that that's equal to 1.0 times 10 to the negative 14. All right. And so, considering thinking the idea of pH and it being a negative logarithmic of this, and so we could actually kind of convert this equation to help us to see this in a better light. All right. And so if we were to take the negative log, and so we take the negative log of everything of Kw equals the negative log of the concentration of, I wrote this wrong. The concentration of hydronium times, right, the negative log of the concentration of hydroxide, All right. So this right here, the negative log of the concentration of hydronium, that's essentially is pH, right? This right here, the negative log of the hydroxide, we call this the pOH. All right, and then the negative log of Kw. Well, remember, Kw is really just 1.0 times 10 to the negative 14. So the negative log of Kw, or negative log of 1.0 times 10 to the negative 14, is 14. So 14 is equal to pH plus pOH. All right. And so this is kind of like another equation to, just in case where if you are so happen to maybe trying to figure out what's the pOH of something, right? And you got the pH, we could use this equation to help us to go from one form to another. All right, so let's kind of spend some time going through some practice problems using these different equations to figure out the either the concentration of hydronium or hydroxide, or we're trying to figure out what is the pH or the pOH. All right, so let's look at this very first example here. So let's say that we're dealing with coffee, right? Coffee has the hydronium concentration of 1.0 times 10 to the negative fifth molar. Now the question is, what is the pH? Well, we know the equation for pH is equal to negative log of the concentration of hydronium. All right, and so because we know the concentration of hydronium here, we could actually substitute this number for this right here, and then we could rewrite it where the pH is equal to the negative log of 1.0 times 10 to the negative fifth. All right, and now if you plug that in the calculator accordingly, we find that the pH is 5.0. So that would be the answer to this problem. So let's look at another example here. Well, lemon juice has the pH about 2, all right? And so what would be the hydronium concentration of this? Okay, well, I said earlier, we know that the concentration of hydronium is equal to 10 to the power of negative pH, all right? And so if that's the case, we know what's our pH here because we said that the pH is 2, all right? And then so we'll plug in that 2 here, all right? And so if we know that, then we could say that the hydronium ion concentration is 1 times 10 to the negative 2 molar, all right? And so that would be the answer to this problem. All right, so let's look at this next example here. So we have like a cleaning solution that has the concentration of hydroxide to be 1 times 10 to the negative 3. All right, and now the question is, what is the pH? Now, this question seems easy, but there's several things that you have to think about before you jump into this. And this question is not really as straightforward as it may seem. Okay, and so what do I mean by that? So let's look into all the equations that we've talked about. So we know that pH is equal to the negative log of the concentration of hydronium, right? And we actually talked about pOH, and pOH is a negative log of the concentration of the hydroxide. Okay, we talked about how Kw is equal to hydronium, the concentration of hydronium times the concentration of hydroxide, and that's equal to 1.0 times 10 to the negative 14. And then we know that 14 is equal to pH plus pOH. All right, now when you consider what's given to you in this problem, we have the concentration of hydroxide, and I'm looking for pH. Now, if you notice from the 4 equations that we've talked about, there's not a single equation that actually leads us from the concentration of hydroxide to the pH. There's really not. pH, I can figure out the pH from the concentration of hydronium, but I don't know that from this problem, or at least what's given to us. And I could figure out the pOH from the concentration of hydroxide, but the question's asking you for pH. All right. And so by the looks of this, we're going to need 2 different equations in order to get the answer of this. Now, there are actually 2 different ways you could answer this problem. Now, both ways will give you the same answer. It's just kind of, all depends on which way you just think it's easier. But And I guess in this example, I'm going to show you both ways to answer the problem. As I said, it's really going to be kind of up to you how you choose to figure this one out. Okay. And so one way to do it, since I have the hydroxide concentration, okay, I could use this equation here, all right, where Kw is equal to hydronium times hydroxide equals 1.0 times 10 to the negative 14. All right, I could use this to figure out what is my hydronium concentration. Once I know my hydronium concentration, then I could use this equation here to figure out what's my pH, and that's my answer here. So let me show you how this works. All right, so first I'm going to use this equation, okay? So I'm going to solve for hydronium concentration. So if I rearrange this, hydronium concentration is equal to 1.0 times 10 to the negative 14 divided by the concentration of hydroxide. Or in this case, it's going to be 1.0 times 10 to the negative 14 divided by 1 times 10 to the negative 3. All right. And so if that's that, then that means this answer, the concentration of hydronium is it's really not just 1.0, 1 times 10 to the negative 11. Okay. Now I could actually find the pH. Okay. And so because now I have the concentration of hydronium, I could substitute it for this concentration of hydronium. So pH is equal to negative log of 1 times 10 to the negative 11, and that answer would be 11. So the pH of this substance here is 11. All right, so that's one way of doing this. All right, and so now let me show you the other way that you could actually figure this out. All right, and so I'm going to erase all this. I mean, you can always pause, rewind this video if you want to see this step by step. All right, now another way you could do this is that I could actually first find the pOH, okay? And once I find the pOH, I can use this equation to find the pH, okay? So pOH is equal to the negative log of the concentration of hydroxide ion, all right? And so I will substitute this number for this. So pOH is equal to negative log of 1.0 times 10 to the negative 3. I don't know why I keep on writing 1.0, it's just 1. All right, and so that means the pOH here is 3, all right? And so now that I know my pOH is 3, I could substitute this 3 for this pOH in this equation, all right? And I'm going to solve for pH. So in this case, pH is equal to 14 minus pOH, or it's 14 minus 3, which is, once again, 11. All right. And so, as I said, there were just multiple ways that you could have just answered or figured out this question specifically.